Okay, so now we're going to talk about trusses. And really what trusses are is a large structure that's comprised of slender members connected to their joints. For example, over here in the picture we have a bridge, and we have these slender members connected together at their joints. Okay. Now, at each of these joints, they're at least modeled as pin connections. In real life, oftentimes they use gusset plates with rivets and things of that nature, but for our models and to simplify the model, we use pin connections at the joints. The other thing that we do that simplifies our modeling of these trusses is that we assume all of the loadings are applied at the joint, so at all of these pins. So even though I have a load that goes over the entire beam, I would separate that out and simply put the loads at the at the connection at those joints. So not only those loads, but the weights of the members are ignored. So rather than dealing with the weights of the members, I just put any loads that I have at the pin joints. Now, these two things, the fact that the joints are pin connections and that all the loadings are applied at the joints, create that these members are two-force members. Okay, and we've talked about two-force members in the past. So each member is either in tension or compression, because again, if they're pin joints, I just have forces here. I don't have any moments acting at the endpoints. Okay, and if the loadings only occur where the pins are, then I only have forces at each of the two pins. So it's a two-force member. So if it's in tension, obviously it's elongating. If it's compression, it's shortening. Okay, and this idea that our trusses are made up of two-force members very much simplifies the analysis of these structures. Okay, now the simplest rigid truss is a triangle. Okay, because with these pin connections, slender members, a triangle is a perfectly rigid structure, assuming that the members are rigid and things of that nature. So you'll see most of the trusses are comprised of a series of triangles. Okay, now let's get into how we actually model this. And the first way that we're going to discuss how to do it is through the method of joints. Okay, and this is really the best method to use when every member in your system needs to be figured out. Okay, next time we'll talk about a separate method if you're just trying to find a couple members somewhere in the middle of a large truss. But if you're trying to find every member in a truss, really the method of joints is the best way to go. Okay, so the first step is to find the reactions, okay, that are occurring on the entire truss. So basically, in a problem like this, what's going on at A and what's going on at C, right? I've got a pin over at A and I've got a rocker over at C, okay? Really, the only external force is the 500 newtons. Don't make the mistake of including all the member forces, because again, those are going to be internal to the entire truss, okay? So that's always the first step, is to find that. And you do that just by summing the forces, summing the moments, using those equilibrium equations for the entire truss that you have here. Okay, and a lot of times this step can be skipped, but it's always good practice to do it, because sometimes you're going to need it. Okay, so find those reactions. Okay, so now to go through the method of joints, what you want to do is, after you have all of your external forces figured out, you want to draw a free body diagram of a joint with at least one known force and at most two unknown forces. Okay, so for what we have here, we look at joint B, because I have one known force, 500 newtons, and no more than, I just have these two unknown forces, and that's because I'm only going to have two equations, so I can only solve for up to two unknowns for each joint. Okay, so when I look at that joint, the member forces actually become external to the joints, because I'm actually drawing the free body diagram of the joint, not of the truss. So if I look at joint B, I have 500 newtons acting on it, as well as the member BC, and since it's a two-force member, I know its direction. I also have member AB, which is also a two-force member. So again, I know its direction. I don't necessarily know whether it's tension or compression, so I can just guess if I want to. Okay, tension is going to be pulling on point B, because remember, I'm looking at the force on the pin, and that member is pulling on the pin, as opposed to if the member is compression, as shown here in BC, it's pushing in on the pin, because I'm drawing the free body diagram of the pin. Okay, so arrows out, like AB here, are tension. Arrows in, like BC, are compression for that member. Okay, the way I typically do it is I always assume tension. Okay, unless I have good reason to assume compression. That way it just keeps my thoughts very consistent, and again, if I get a positive answer, my assumption is correct. That way I always know that a positive answer is tension, and a negative answer, which means my assumption of tension is wrong, means compression. Okay, but you can really draw it any way that you want, but I always tend to assume tension, and then if I get a negative answer, my assumption was incorrect, I get compression. Okay, once you have your free body diagram of the joint drawn, so you've got any external forces and then any member forces acting on that joint, you go ahead and you apply your sum of the forces in the x and y direction. Now I won't have a moment equation because all of the forces go through the same point, so there's no moment arm. So I only have the sum of the forces in the x and y. That's why I cannot choose a point that has more than two unknowns in it, because I only have two equations to solve for those two unknowns. Okay. Once I finish that, I move on to the next joint. I look for a joint that has, at least one known force and no more than two unknown forces. And I draw a free body diagram at that joint, and I move piece by piece through the truss to solve each force in the truss.